sweet math video, specifically on calculus. So welcome back, math neighbors. This is from the related rates practice, the homework section, number 27. This is a very difficult problem to picture. And remember what I mean by picturing is I don't mean sketching a picture, I mean getting a mental picture of the situation so that you're able to interpret, understand, and eventually solve the math. So we've got the infamous shadow problem. This is one version of it. A spotlight is on the ground 21 feet away from a wall, and a 6-foot tall man is walking towards the wall at a rate of 2 feet per second, as shown in the figure to the right. And then we're going to answer two questions. The first one, how fast is the height of the shadow changing when the man is 6 feet from the wall? Second question, how fast is the angle of elevation changing at that same time? So I drew a slightly different picture that you may be able to see here. And I'm going to pause real quick and remind you one of the best things about working with videos is the ability to pause them. So that's all of the work for this particular question, both parts. Pause the video if you don't want to listen to me go on and take advantage of that freedom of video. Otherwise, here we go. So I tried to picture the situation by literally picturing the situation. So I said I've got a spotlight here, and the spotlight goes and then to the ground, and then there's a wall, and you'll notice I crossed out wall. That was purposeful because we're not actually interested in the wall. We're interested in the shadow of the man on the wall. So you can try this out at home. Put a light on the floor behind you and then walk away from light towards the wall. And you'll notice what happens is as you do that, your shadow gets shorter as you get closer to the wall. So that may help you picture what's going on, maybe not. But anyway, we've got a 6-foot tall man, and there are some relevant distances here. But in order to understand those relative distances, we're going to start off with this idea. So what I did was I used an old trick from geometry. And when I've got overlapping triangles like I do here, I know that they are similar triangles. So because they're similar triangles, all of their features are proportional. Sorry, not features. Side lengths are proportional. The angles are congruent. So I took the big triangle, which starts at the spotlight, goes along the ground to the wall, not up the wall, but up the shadow, and then light beam back. Then we got a smaller triangle overlapping that one, a distance from the light to the man along the ground, the height of the man, and then from the light beam to the man. So because these are proportional, we can make this statement here. The distance, or the length of the shadow, is shadow to ground, that horizontal, that's going to be equal to the height of the man and then the distance from the man to the light. So the picture that you were given in the problem called that x. I just decided to call that x. And then we have dx dt. dx dt is the change of the distance between the man and the light. Now, in order to solve this ratio, we need a bunch of useful information. And some of that useful information comes from calculating, and some of that useful information does not come from calculating. So let's talk about the useful information. So the first ones I noted over here. The height of the man and the distance from the light to the shadow are not changing. The spotlight is fixed, and then the man's height is fixed, and then since the spotlight is fixed, it's not getting any closer to the wall. So those are all 0, or those are both 0. All right. So we're talking about this relationship, shadow to the distance between the shadow and the light, 21. That's proportional to the height of the man, 6, and the length of the distance between the man and the spotlight, which was called x. Now I did make a mistake here. I did 6 times 12 was 72. I obviously thought that 12 was, or that was a 12 rather than 21. It's actually 126, so sorry about the typo. But the math here remains the same. So I cross-multiplied a little bit. I multiplied both sides by 21. And the reason why I did that was because on the right side then I had 126x to the negative first power, whose derivative with respect to t is negative 126 divided by x squared times the derivative of x with respect to time dx dt. And I just said that the shadow is s, ds dt, that's what I'm solving for, is the rate of change of the length of the shadow. Then I substituted in for x 15, because that's 21 minus 6, that's the total distance minus the 6 feet the man has walked. And dx dt is getting larger at a rate of 2 feet per second. I substituted those in and simplified. I got it negative 1.120 feet per second, which comes up in part B, because in part B we're talking about the angle of elevation. So the angle of elevation is the angle at the spotlight, and that covers from the ground all the way up to the top of the shadow. So this is at the same time. So if I differentiate with respect to t, tangent of theta is secant squared of theta d theta dt. On the right side, I use the quotient rule. I called g the ground, s the shadow, so I have ds dt and dg dt. And then I used a bunch of information like so. In order to solve for d theta dt, I need theta, I need g, ds dt, s, dg dt, and there's g again. But I actually don't need all of that. I already said that dg dt is 0. Why is that? Because the length along the ground from the light to the wall where the shadow is doesn't change. So that's 0. That distance is 21. Because that's 0, I don't actually need to calculate s. I suppose I could, but I'm not going to, because this second term in the numerator is 0. And I already know what g is, so that just means I need to figure out what theta is. And there are a couple of different ways you could get theta. What I decided to do was use the small triangle. So that's this triangle here. And I know that the height of the man is 6, and the distance between the light and where the man is at this exact time is 15. So inverse tangent of 2/5 is 0.381, which I stored. And I've done all of the hard work, and I solved. And instead of writing dividing by secant of 0.381 squared, I just had multiplying by cosine of 0.381 and then squared. And then I was feeling fancy, so I said ds dt was the negative 252 divided by 225, which again was the answer from A, divided by 21, which is g, times that value gives me the 0.046 radians per second. And then I was feeling super fancy, so I decided to show you how to get the exact value of the cosine of the inverse tangent of 2/5, which I did down here. So if you wanted to stop watching the video right now, that's fine. There's no calculus to speak of. Just an interesting bit. So arctangent of 2/5 is the angle theta, whose opposite to adjacent ratio is 2/5. I can use the Pythagorean theorem to say that this is 4 plus 25. The square root of that is 29. Then when I take the cosine of this angle, it's 5 over the square root of 29. And you'll see if you square 5 over the square root of 29 and multiply it by this fraction, you get the same thing. Thanks. Enjoy. Etc. etc. YouTube, Twitch nonsense. See you guys.